Okay, welcome everybody back. So let's proceed to our second speaker today. So our second speaker today is Fei Pu from the University of Luxembourg. Fei got his PhD in 2018 at EPFL under the supervision of Robert Dallon. He then moved to the University of Utah as a postdoc before he further moved to the University of Luxembourg to do a second postdoc this year. So we're very happy to have you here, Fei, and look forward to your talk, Ergodicity and central limit theorem for the parabolic Anderson model with delta initial condition.
Okay, thanks, Carsten, for introduction. If I really pay to my research work here, I will also talk about ergodicity and the COT for stochastic head equation, as in the last talk. So here the difference is that I will only focus on the delta initial condition. So we will say that how this delta initial condition affects the ergodicity and the COT. So this is based on joint work with my co-authors, Chen, Devan, and David. All right, now let's look at the parabolic Anderson model. So this is a spatial stochastic head equation. So in this equation, U of Tx denotes the solution to parabolic Anderson model. And here eta denotes the space-time values. And here we only consider X in R, we only consider the one-dimensional case. And we will show that when T is equal to 0, the solution starts from the Dirac Mayor at 0. So U of 0 is equal to delta 0. So this is a delta initial condition. The mapped solution to parabolic Anderson model satisfies the following stochastic integral equation. So in this equation, we have U of Tx is equal to Pt of x plus this stochastic integral. So here, Pt of x denotes the head column, which is the density of standard Brown motion at t. In this integral, we have this integral is in fact the space-time convolution between the head curve and the solution and the space-time values. And this quantity is in fact it comes from the initial condition. We know that the convolution between the head curve and the Dirac Mayor give us the head column. So this one, it comes from the delta initial condition. For a solution to parabolic Anderson model, in the paper by Amick, Coven, and Quastel, they prove that if we scale the solution by the head column, so for this process, the process in space, this is a stationary process for every t per t. Okay, so the solution to parabolic Anderson model give us a stationary process in this way. And we know that in general, for stationary process, we have the Birkhoff and the von Neumann ergodic survey. It says the following. So for this process, if we integrate over an interval and then we divide by n, this is the spatial average. So if n goes to infinity, this spatial average it converges to the conditional expectation. We have E of U of T0 over Pt of 0 given I. So here I denotes the invariant sigma algebra of this stationary process. So this is the ergodic survey. So here let me recall that we say that a stationary process is ergodic if and only if its invariant sigma algebra is trivial. So here I is trivial means that P of A is equal to 0 or 1 for any set A in I. So this is the definition of ergodicity. So here, one remark is that the ergodicity implies law of natural numbers. So this is because if this process is ergodic, that is to say, if I is trivial, then in this ergodic survey, this conditional expression becomes expression. And that gives us the spatial average converges to the expression. And this is law of natural numbers. All right, so this is some basic information on this parabolic Anderson model with delta initial condition. So our first result is the ergodicity. We prove that this process, if we scale the solution to parabolic model by the head column, this process is ergodic for every t per t. So we prove the ergodicity. And as a consequence of ergodicity, we have the following law of large numbers. So we have the special average, it converges to the expectation, which is equal to 1. This is law of large numbers. All right, so in the following, let me show you some elements for the proof of ergodicity. The first one is the Clark-Orco formula. We have seen this formula in the last talk. So we can write f as e of f plus this stochastic integral with respect to space-time values. In the integrand, we have the conditional expression. So here, dsyf denotes the Maillard derivative of f at this point sy, and fs denotes the sigma algebra, the filtration generated by the space-time values. This is a Clark-Orco formula in the case of space-time values. Now, from this Clark-Orco formula, we can derive the following inequality, which is called Poincare inequality. So here, we choose two variables, f and g, and look at the covariance between f and g. So from this formula, the covariance between f and g is equal to the expression of two, it is equal to the expression of the product of two stochastic integrals. And then we can use ethos isometry and some inequalities such as Holder inequality and the Jason's inequality. And we can bound this covariance by this integral. In the integrand, we have the Maillard derivative of f. Here we take the L2 law. We have the Maillard derivative of g. We also take the L2 law. So this is the Poincare inequality. You see, in this inequality, we have to compute the Maillard derivative of the variables. So for the solution to parabolic model, we can also compute the Maillard derivative. In fact, we have the following estimates. So here, the Maillard derivative of u of tx at this point, Rz, we look at the LK law. This is bounded about by constant times pt minus r of x minus z. This is the head column times pr of z. We have this upper bound for the Maillard derivative of a solution to parabolic model. We can compare this estimate with the case of constant initial condition. So if u of 0 is equal to 1, we prove that the Maillard derivative of the solution at Rz, it is bounded about by constant times pt minus r of x minus z. So you see, we can compare these two inequalities. In this case, if we have Dirac-Miller initial condition, then for the Maillard derivative, we have two quantities, we have two head colors. So this is very different from the stationary case. Okay. So in the following, I'm going to show you the proof. For the simplicity, I will only show the proof for the law of large numbers. All right, let's look at the proof for this L2 convergence. So now we look at the difference between this special average and the constant one. And we look at the second moment. So first of all, the constant, we can put it inside this integral. And we take a square, it gives us a double integral, dx dy. And then in the integrand, we have the product of these two variables. So moreover, we can put this expression inside this integral, and that gives us the covariance between these two variables. Okay, I mean here we just exchange the expression and this double integral, and the integrand give us the covariance between these two variables. And now for the covariance, we can use the previous Poincare inequality to estimate. Okay. By Poincare inequality, we have the covariance between these two variables. It is bounded above by the integral in time, the integral in space, and in the integrand, we have the Marian derivative of these two variables. So here, since these two head colors, they are deterministic. So in the numerator, we only have the Marian derivative of the solution. Okay, so here we have two quantities. Now, as I said before, we can estimate the Marian derivative of the solution. In fact, we have this L2 node, it is bounded above by the head color pt minus r of x minus z times pr of z. Okay. Similarly, this Marian derivative, it is bounded above by these two quantities. So you see, in the end, when we use Poincare inequality and the estimate of the Marian derivative of the solution, in the end, we have a deterministic integral in terms of head colors. So you see here we have 6 terms. So we can do some computation with the head colors. In the end, this integral, it is bounded above by constant times log n over n. And this one, it converges to 0 as n goes to infinity. And this proves the convergence in L2, which gives us law of large numbers. Okay, so you see, the main elements is the Poincare inequality and the estimate of the Marian derivative of solution. I mean, for the ergodicity, the proof is kind of similar. We still use Poincare inequality and the estimate on the Marian derivative of solution. So in the end, we can still compute the covariance, and that gives us ergodicity. All right, so this is some basic computation on law of large numbers. Now let's look at the central limit theory. So here, I introduce a new notation, SNT. SNT is called the centered average. So it is defined as 1 over n times this integral. So this is the centered variable. In the previous slide, we proved that the second moment of SNT it converges to 0. In fact, in the previous slide, I should use that the second moment of SNT it is bounded above the constant times log n over n. In fact, we can have precise estimate on the second moment of SNT. We prove that as n goes to infinity, the variance of SNT, that is to say, the second moment of SNT behaves as 2t times log n over n. Okay, so you see, here we have the precise limit for the variance of SNT as n goes to infinity. All right, now for this centered average, we can normalize in the following way. I mean, here we multiply by square root n over log n. This gives us a normalization, which is equal to 1 over square root n times log n times this special integral. Okay, so here, I mean, this equality, we just use the definition of SNT. And this is the normalization of special integral. And this normalization, we prove that it converges in distribution to a centered Gaussian distribution with variance given by 2t. So this is our COT. I mean, this is really different from the constant initial case. I mean, in that case, we only have to normalize by 1 over square root n. But here, we have to normalize by n times log n. We have this quantity log n. This is different. Okay. Furthermore, for this COT, we can also compute the convergence rate. So what we have is the following. We look at the total variation distance between the normalization and the standard Gaussian distribution. So here SNT divided by square root the variance of SNT. This is the normalization. And the DTV denotes the total variation distance. The definition of total variation distance is equal to the supplement of the Borel set. Here we have the difference of two probabilities. We prove that the total variation distance between this normalization and the standard normal distribution, it is bounded above a constant times square root log n over n. Okay. So first of all, we know that the convergence of total variation distance implies convergence in distribution. So therefore, this estimate, this inequality implies this CLT. Okay. This is because we know the behavior of the variance of SNT. Okay. This behaves like 2t times log n over n. So therefore, this convergence rate implies the CLT. By the way, this convergence rate log n over n, this one, it is consistent with the behavior of the variance of SNT. This convergence rate, it is a natural convergence rate that we expect. All right, so now we only have to prove this inequality. So we will use the Marley-Weinstein method to prove the estimate on total variation distance. So this is our goal. We will use Marley-Weinstein method to estimate the total variation distance. So here, let me state a theory by Northern and Picardi. So this theory appears in the last talk. So let me repeat it again. So here, assume f is Marley-Weinstein differentiable, and f has the second moment of f is equal to 1. And moreover, f can be written as delta of v. So here delta denotes square root integral. We can understand delta is the stochastic integral. Okay. Then we have the following inequality. We have the total variation distance between f and the standard normal distribution. It is bounded above by 2 times square root the variance of the inner product between df and v. So we have this inequality for total variation distance. So here, let me point out that Huang Niala and Vitasawa, they are the first to use Marley-Weinstein method to prove central limit theory for stochastic head equation. So in their paper, what they have is U observed it is equal to 1. In their case, the initial condition is equal to 1, and the solution is a stationary process. And here, we will use this Marley-Weinstein method to estimate the total variation distance in the case delta 0 is equal to, U0 it is equal to delta 0. Okay. All right, so now let me show you how to apply this inequality. So first of all, we will choose f as this normalization, SNT, over the square root of the variance of SNT. So this is our f. This is our candidate for f. Of course, f has, the second moment of f is equal to 1. And we can prove that f is Marley-Weinstein differentiable. And then now let me show you that f can be written as delta v. F is in fact equal to a stochastic integral. So first of all, we use the definition of SNT to write this one, it is equal to this constant times 1 over n times this, the bigger integral. So this is the definition of SNT. But now for this special integral in the integrand u of tx over pt of x minus 1, this integral we can write it as the following integral. Okay, this one is in fact equal to this stochastic integral. So here we only use the mad form of solution to have this equality. Okay, I mean, the solution to parabolic answer model satisfies the stochastic integral equation. We use that equation to derive this integral is in fact equal to the stochastic integral. So here we have the specified value is eta. We say now we have two integrals dx, the special integral. We have the stochastic integral eta ds dy. Now for these two integrals, we can switch the orders. I mean, we use stochastic Fubini theory to switch these two integrals. This is equal to the stochastic integral, and in the integrand, we have this special integral. So you see, in the end, we can write f as a constant times a stochastic integral. So therefore, f is equal to delta v, and delta and v, this integrand v is equal to this constant times this integrand. So you see, we have this formula for v, and moreover, we also have this formula for f. So therefore, we can compute the inner product between df and v using these two formulas, and then we can compute the variance of this inner product. In the end, we can bound this variance by a constant times log n over n, and that gives us the estimate on total variation distance, and hence we can prove COT. Okay. So this is how we apply Malerman state method to study the COT for stochastic heat equation. So here I do not show you the computation for the variance. I mean, in the computation, we will still use the Poincare inequality and the estimate of the Malerman derivative. In the end, we have such a bound for the total variation distance. All right, so in the end, let me propose some related problems. The first problem is the parabolic answer model with time-independent Gaussian noise. So this is our parabolic answer model. U is the solution, and V is our noise. But in this equation, this noise does not depend on time. Okay, we only have X variable here. So the question is, can we also study the ergodicity, the stationarity, ergodicity, and the COT for this process? I think for the stationarity, I think this is true because you can always use the Feynman-Clark formula to say the stationarity. But for ergodicity and COT, I think it's different. Okay, I don't know how to do this for ergodicity and COT for this time-independent Gaussian noise. So this is one question. Another question is the COT for the capital equation. So here, let me introduce a new process. I use H to denote log of U of x over PT of x. So this new process is related to the capital equation. So we know that this process is ergodic for every t positive. Okay, and this is because this process is ergodic, and this function log does not change. It does not change the sigma invariant. So it does not change the invariant sigma interval. So therefore, H is ergodic for every t positive. So as a consequence of ergodicity, we have law of natural numbers. The problem is, can I also prove a COT for this process H? So here, let me show you the central limit theory for the capital equation in the case U0 is equal to 1. In this case, the solution is a stationary process. We proved the following COT for the capital equation. So here, the integrand, we look at log of U of tx, we subtract its expression, and then we take the integral and divide it by square root n. So this is the normalization. We prove that this normalization, it converges to a centered normal distribution, and the variance sigma t squared is given by this integral. In the integrand, we have this covariance function, and we prove that this covariance, so this variance, it is strictly between 0 and infinity. So this is the CLT in the case, I mean the CLT for KPZ in the case U0 is equal to 1. The question is, can we also prove a CLT for this process H? Okay. So these are some related problems that I'm considering. All right, so this is all the material that I want to present. I stop here. Thank you very much for listening.
Thanks a lot, Fei, for your very nice talk. We have time for one very quick question. Does anybody have a question from the audience? I have a question. So do you have an intuitive explanation why you get this extra log term in the case when you have a delta initial condition?
Well, so first of all, it was proved by Ampere et al. That this process is stationary, and at the beginning, we want to know if this stationary process is ergodic, and therefore we have to compute the variance. When we compute the variance, we found that we found the log n. We found this quantity log n.
But do you have an intuitive, descriptive explanation why this happens? So
I don't know that.
Or does it come out, or is it only that comes out from the calculation?
Yeah. Otherwise, you can also say from this equation, if you divide by the head curve in this equation, that give us a constant initial condition equation. I mean, it gives us a new equation. I mean, if you look at this equation, if you divide both sides by the head curve, it gives us a new equation, and that equation starts from 1.
Mm-hmm. Okay. So if there are no further questions, let's thank both speakers today again. And I want to draw your attention to, so we have another talk next week, same time, and it will be by Kevin Young, talking about KPC equation coming from long-range interacting particle systems. Okay, so thanks again for joining us today. I will now conclude the session. So have a nice Friday and have a nice weekend. See you all. Bye-bye. How do I do this?